So Raoult's law for volatile solutes. So the same principles still apply. If there's less solvent, then there's going to be less pressure, no matter whether it is volatile or not. But what you can have is both of them in the vapor phase, right? So the total vapor pressure above the solution will be the sum of the vapor pressures of the solute and the solvent. They'll act essentially independently if Raoult's law holds. So for an ideal solution, that's a solution where their interactions are essentially equal, so they don't really care how much, whether you're next to the solute or solvent, the energetics are exactly the same. So for an ideal solution, then the total partial pressure is equal to the partial pressure of the solute plus the solvent. So this is an expression of both ideal solutions and just Dalton's law of partial pressures. So the solvent decreases the solute's vapor pressure in the same way the solute decreases the solvent. That's why, when it comes down to it, what's the minor component, what's the major component, it doesn't really matter. They're all interacting with each other. So what we'd see is the vapor pressure is the solute is vapor pressure of the solute is mole fraction solute times the partial pressure of the pure solute, and the partial pressure of the solvent is mole fraction solvent times pure partial pressure solvent. Okay. So that's an ideal solution, but most solutions are non-ideal. They're non-ideal because it actually matters whether a solute is next to a solvent or next to another solute. So in ideal solutions, the made solute-solvent interactions are equal to the sum of the broken solute-solute and solute-solvent interactions. Ideal solutions follow Raoult's law, i.e. effectively the solute is diluting the solvent and vice versa. But if the solute-solvent interactions are stronger or weaker than the broken interactions, the solution's non-ideal. If the solute and solvent like each other more, or if they really don't like each other and they're only mixing because entropy made them mix, then the solution will be non-ideal. So what would the vapor pressure of a non-ideal solution look like? So when the solute-solvent interactions are stronger than the solute plus solute-solvent interactions, then the total vapor pressure will be less because the molecules really don't want to leave because they're nice. They've just met their nice buddy solutes/solvents and don't want to leave the solution. They're attracted into the solution. When the solute-solvent interactions are weaker than the solute-solute plus solvent interactions, then they want to get out, right? They're only in there because entropy is making them. They're happy to escape from the solution. There's less interactions pulling them down. So the vapor pressure of the solution will be more than predicted by Raoult's law. It's more volatile. So what you get is something like this. And you'll see a lot more of these charts in chemical engineering thermodynamics. But for an ideal solution, they're essentially just sort of acting independently. An ideal gas, the different gas mixtures don't even see each other. An ideal solution, they do see each other, but they treat each other exactly the same. And so the vapor pressures will just be as if they were alone by themselves. And so if this is the vapor pressure of pure B, the vapor pressure of the solution, the vapor pressure will be the combined vapors of A and B, will just be a linear combination of what you get in A and B. The vapor above the solution will have the same composition as the liquid will. If you have strong solute-solvent interactions, you'll get a lower total vapor pressure. Each of the components will contribute less, and the sum will be less. And if you have weak solute-solvent interactions, then you get excess vapor pressure. Both the solute and the solvent want out because the mixture interactions are not enough to pull them in. So you'll have behavior like that.